In this video, we discuss lesson 8.1, learning outcome number 1, which is all about the big picture of hypothesis testing. Here we're going to define some essential terms related to hypothesis testing, including claim, hypothesis, null hypothesis, and alternative hypothesis. My goal for you is that you'll be able to describe hypothesis testing in your own words and how it relates to the rare event rule and sampling distributions. And another goal that I have for you is that you'll be able to identify the null and alternative hypotheses associated with a given claim. Now, by the end of this video, you will not be able to conduct a hypothesis test. Not yet. We're going to need a couple of more videos to discuss the details of this big picture. But once we get through a couple more videos, we'll be able to conduct hypothesis tests, and we'll hopefully truly understand what everything means. Everything that we're doing is meaningful, and it's related to ideas that we've studied in previous sections. It's all just an extension of that. So you might be thinking, okay, I know what a hypothesis is. Well, in statistics, what a hypothesis is a claim or a statement about a property of a population. So it's going to be a claim or a statement about some population parameter. Maybe you are making a claim or a statement about a population proportion or a population mean or a population standard deviation or a population variance. All of those may be hypotheses in different hypothesis tests. A hypothesis test is also known as a test of significance, and this is just a formal procedure for testing a claim about a property of a population. Now, this is all based on some ideas that we've talked about earlier. We discussed the rare event rule for the first time in lesson 4.1 in our 4th video. And then we discussed sampling distributions in great detail in lesson 6.3. And we elaborated on that when we talked about confidence intervals in chapter 7. Our understanding of those confidence intervals, sampling distributions, and the rare event rule are going to help us to understand exactly what it is we're doing as we conduct a hypothesis test. These form the foundation of all of the ideas that we'll study in chapter 8, chapter 9, and in chapter 10. Okay, so here's an example. It's relating to your personal online data. So here's a claim. It says some claim that most adults would erase all of their personal online information or personal information online if they could. I am one of them, definitely. A GFI software survey of 565 randomly selected adults showed that 59% of them would erase all of their personal information online if they could. Then we're told to let P denote the proportion of adults who would erase all of their personal information online if they could. Now we're supposed to identify the claim. Well, the claim is just that first sentence, but we want to write it in symbolic form. So it says some claim that most adults would erase all of their personal information online if they could. Most just means the majority, and the majority means more than 50%. So the claim is that P is greater than 50%, or in decimal form, that's P is greater than 0.5. So that's the symbolic form of our original claim. Now, if we want to test this, we can use the hypothesis testing procedure that we're going to talk about in this lesson and in the next lesson. 8.1 is about testing claims about proportions. And we're going to get into a lot more detail about that. So the question is it true that most adults would erase all of their personal information online if they could? And if it is true, is the fact that that sample of 565 randomly selected adults had 59% of them agreeing with that statement that they would erase all of their personal information online if they could? Is that 59% enough evidence to suggest that most adults would erase all their personal information online if they could? That's what hypothesis testing is about. It's taking that sample information from those 565 randomly selected adults and looking at that that sample proportion of 59% and saying, okay, if I know I've got 59% from this particular sample and this sample had a size of 565, can I say that most adults would erase all their personal information online? can I make a statement about this claim? Okay, so in order to do that, the first thing that we do is we write the claim in symbolic form, just as we did on the last slide, and then we use it to infer the null and alternative hypotheses. These are statements about a population parameter, such as a population mean, standard deviation, or proportion. Now, the null and alternative hypotheses are something that will have to be identified by you. The null hypothesis is denoted by H sub 0, or sometimes that's pronounced H naught. And this is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. The alternative hypothesis is a statement that the parameter has a value that differs from the value in the null. So if the null is saying that it's equal to some value, the alternative hypothesis is saying it's not equal to some value in some way. It might just say it's not equal to it, or it might say that value is, or the population parameter is greater than that value, or it might say that the population parameter is less than that value. All of those are fine alternative hypotheses. So you're going to see a less than sign, a greater than sign, or not equal sign in your alternative hypothesis. Now, here's just a step-by-step process to identify the null and alternative hypotheses for a given problem. First, you want to state the claim in symbolic form. And then you want to think about what would have to be true if the claim isn't true. And then you look at those two statements. One's a claim and one is true if the claim isn't true. And you look for the one that does not contain the condition of equality. So it's going to be a less than sign, a greater than sign, or a not equal to sign. That's the alternative hypothesis. And then the null hypothesis will always have an equal sign in it. So you just change the less than, greater than, or not equal to sign from the alternative into an equal sign, and that's going to give you the null. So let me show you what I mean. So in this example, it says identify the claim and the null and alternative hypotheses. We already know that our claim is this top line. It said some claim that most adults would erase all of their personal information online if they could. That's saying most adults is saying that the proportion is greater than 50%, or the proportion is greater than 0.50 in decimal form. So that is our original claim. And then we say, okay, if the original claim isn't true, what if P is not greater than 0.5? Well, then P would have to be less than or equal to 0.5. And then you look at both of those and you say, okay, which one contains the condition of equality and which one doesn't? This top one, I'm getting my annotation stuff out. This top one does not contain the condition of equality. Some students are like, what do you mean contain the condition of equality? This one down here, this one contains the condition of equality, because this is saying that P is less than 0.5 or P is equal to 0.5. It says less than or equal. So the one that we're looking for, the one that does not contain the condition of equality, that's the alternative hypothesis. And that's this top one up here. And then we say the null hypothesis always includes an equal sign. So we change that greater than sign to an equal sign, and that's the null. Okay. Okay, so the first thing we do is we do that. We state the claim in symbolic form. We use it to infer the null and alternative hypotheses. And in our example, our claim was that P was greater than 0.5. The null is that P is equal to 0.5, and the alternative is that P is strictly greater than 0.5, which happened to be our claim. And then the question becomes, whenever you're doing a hypothesis test, if the null hypothesis is true, is the value of the sample statistic, that 59% of our sample that said that they would erase all of their data online if they could, is that value of the sample statistic, is it extreme if this null hypothesis is true? So if it is extreme, then we'll say that's very rare, that shouldn't happen. Therefore, we should reject that initial assumption that the null hypothesis is true. And then if we say, if we're assuming that the null hypothesis is true, and then we say that the sample statistic value is not extreme, then we say, okay, well, maybe the this variation that we're seeing in the sample statistic is just due to chance. So we can't claim anything about the null hypothesis. Say it's not being contradicted by the evidence. We're not able to say that the null is true. We're not able to say that it's not true, but we're just not going to reject it as a possibility. Okay, I know that that's a lot. So keep thinking about that, and we're going to come back to that over and over again. And I think that through some repetition and some examples, you're going to get it. You're going to get it really well. Okay, so in order to test these hypotheses, what you're going to have to do is first identify and compute the sample statistic and the sample size n. You want to write those down, and then you want to graph a sampling distribution of that sample statistic, assuming that the null hypothesis is true. And then you want to label that sample statistic on the graph and say, this particular value from my sample, is it extreme given that I'm assuming that the null hypothesis is true? If it is extreme, maybe the null hypothesis isn't true. So let's do that for this example. It says state the sample proportion and the sample size. Well, the sample proportion, that's represented by p hat. That's going to be 59%, but we're going to write that in decimal form, so that's 0.59. And the sample size is those 565, that's our n. Those are the 565 randomly selected adults that were surveyed. And then after we do that, we want to graph the sampling distribution of the sample statistic, assuming that the null hypothesis is true, and then label the sample statistic on the graph. So our null was that p is equal to 0.5. And the original claim was that p is greater than 0.5. Now remember what p represents. P is the proportion of adults who would erase all of their personal information online if they could. So when we're assuming that the null is true, we're saying that the proportion of adults who would erase all of their personal information online if they could is 50%, or 0.5. And we're wondering, can we reject that idea that that proportion is 50% or not? In order to do that, we need to look at that value of p hat from our sample. That was the sample proportion. 59% of the adults in that sample said that they would erase all of their personal data if they could, personal information online if they could. And the sample size was 565. Now, a lot of students say, why even point out the sample size? Remember how sampling distributions work. We talked about this back in chapter 6. We said that the way we came up with this sampling distribution is we thought about all of the different ways that we could sample from the general population, 565 randomly selected adults. And I said, okay, let's do that and then compute a sample proportion. And then let's put those 565 people back in and then compute a sample proportion again. And then let's put those guys back in and compute a sample proportion again. And we do this lots of times, as many times as possible. And then we look at the distribution of those sample proportions. Now, we said back in lesson 6.3 that the sample proportion is an unbiased estimator. So what that means is that the mean of the sample proportions is the actual population proportion. It's exactly what we want it to be. So when we draw the sampling distribution over here, we're going to say, okay, let's just assume that the null is true, or let's just assume that the true population proportion, that's the true proportion of people in the population who would erase all of their personal information online if they could. Let's assume that that's equal to 50%. And then we say, okay, that means the mean of this distribution, the sampling distribution, which is approximately normal for sample proportions, is 50% or 0.5. Then we want to graph that p hat. P hat is 0.59. That's more than 50%. We're saying to ourselves, is 59% enough to suggest, at a statistically significant level, that most adults, more than 50% of adults, would erase all of their personal information online if they could? If that p hat was about 51%, we'd say, oh, that could happen due to chance. Or if p hat happened to be 99%, we'd say, Yes, definitely. It's definitely the case that most adults would erase all of their personal information online. But then we say, what does this 59% mean? Is that enough evidence to suggest that the true population proportion is actually more than 50%? And we're going to decide whether that's enough evidence to suggest that by thinking about whether this 59%, this p hat of 0.59, is rare, given the assumption that the null hypothesis is true. That means that the proportion in the population that would erase all of their personal information online if they could is exactly 50%, or 0.5 if you prefer. So we're saying to ourselves, is this value 59% extreme given our assumption? Is this value, given our assumption, unlikely to occur by chance? Is this rare? If it is rare, we're going to apply the rare event rule. Now, remember what the rare event rule says. We talked about this back in chapter 4. We said if under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less often or significantly more often than what we would typically expect, with that assumption, then we conclude that the assumption is probably not correct. Or in other words, okay, we're assuming something is true. In this case, we're assuming that the null hypothesis is true. We're saying, assuming that that's true, is the probability of getting a p hat like this 59% extremely small? Is it very rare that we would get a probability of, or a sample proportion of 50% if the true population proportion is actually 50% or 59%? Well, the true population proportion is actually 50%. If that's rare, we're going to say it's rare, it's not supposed to happen, but guess what? It's actually happening. If it's happening, and our assumption would imply that it's extremely rare, this should not be happening, then we'll say, oh, maybe our assumption's wrong. And remember what our assumption was in this case. Our assumption was that the null hypothesis is true. So if we get a very rare event happening in real life, we're going to say, let's reject the assumption. And that's rejecting the null hypothesis. Now, if the event that we're seeing happen isn't rare, given our assumption, we're going to say, this evidence doesn't contradict the assumption at all. It doesn't mean that the assumption is correct. It just means that we don't have enough evidence to reject the assumption. We say, oh, you said 50% is the true population proportion, and actually we got 51%. Well, that could easily happen due to chance. So it doesn't mean that the actual population proportion is 50%. It just means that all the evidence suggests that we should err on the side of caution and not make any assumptions about that initial assumption. We're not going to, in that case, we don't accept that the null hypothesis is true. We fail to reject that the null hypothesis is true. We fail to reject the null. So this rare event rule, again, is one of the most important rules of statistics. That's why we started talking about it back in chapter 4, and we revisited it again in chapter 5 and in chapter 6. If something is happening in reality, and it shouldn't be happening because the probability of it actually happening is actually very small, but it's happening, then we say, there must be something wrong with our assumptions. That's the rare event rule, and that's the basis of hypothesis testing. Okay. So we said this is the question. If the null hypothesis is true, is the value of the sample statistic that we found extreme? Is this value unlikely to occur by chance? If the sample statistic is significantly high or significantly low, which corresponds to a very low probability, we're going to say that our initial assumption is likely to be wrong, and then we'll reject the null hypothesis. If the sample statistic isn't extreme, given our assumption, or it could have easily occurred by chance, we can't say anything about our assumption. The sample evidence is inconclusive, and it doesn't warrant rejection of our assumed null hypothesis. So going back to our example, in our example, we're assuming that the population proportion is 50%. So we're assuming that 50% of the population would erase all of their personal information online if they could. And then we're saying, if that's true, if 50% is the true population proportion, how rare is it to get a sample proportion of 59%? If it's very rare, we're going to say, maybe our assumption is wrong, throw out the null hypothesis. If it's not rare, we're going to say, okay, well, maybe the null hypothesis is true. It might be true, it might not be true, but we don't have evidence. We don't have enough evidence to get rid of that null hypothesis. We don't have enough evidence to reject it, so we're going to do something called failing to reject the null hypothesis. And remember, again, we're going to reject explanations that are based on very low probabilities. So we're going to say if something is happening and it's not supposed to happen very often at all, I mean, maybe we're in that case, that 1 in a million case where it's happening. This is just the 1 in a million that we've actually arrived at that 1 in a million. Or we might say, maybe the probability isn't truly 1 in a million. Okay, so let's go back to that procedure and the big picture for hypothesis testing. The first thing we do whenever we are looking at a claim and we want to conduct a formal hypothesis test is we write the claim in symbolic form, and then we use it to infer the null hypothesis and the alternative hypothesis. The null hypothesis contains an equals sign. The alternative hypothesis contains something else, a less than sign, a greater than sign, or a not equal to sign. And then once we have all of that, what we're doing is we're saying, okay, let's look at the sample statistic and use that sample statistic and a sampling distribution to tell us something about that null hypothesis. So we're going to identify a sample statistic. If it's given to us in the problem statement, we just identify it. Sometimes we've got to compute it. They might say, 200 of these people out of this total number of people voted in this way. So what's the proportion? And so you might have to actually compute that proportion p hat. But you either identify it or you compute it. And then you also have to identify the sample size n, because that is a characteristic of the sampling distribution that you'll be looking at. Then you want to, sorry, my phone is making noise. Then you'll want to graph the sampling distribution of the sample statistic, assuming that the null hypothesis is true, and label that sample statistic on the graph. You don't actually have to do this, but I find that visualizing what's going on really helps me to understand what it is I'm doing and why. And then we want to do something called computing the test statistic. That's a z-score, t-score, or chi-squared. It's another type of score related to standard deviations that is corresponding to the value of the sample statistic that you have. Now, if you're wondering, what do you mean? What is this critical, this test statistic corresponding to the sample statistic? I want to show you. Okay, remember this graph? Okay, so we said for population or for sample proportions, this would be the sampling distribution. We said if the sample size is large enough under certain conditions, these sample proportions are going to be normally distributed. We're going to see that bell shape, and it's going to behave like the normal distribution. But this is a non-standard normal distribution. The mean is equal to 0.5 under our assumption. The mean of the sample proportions is equal to that population proportion that we're assuming of 0.05. But again, this is a non-standard normal distribution. So what I can do is I can say, okay, given this assumption, what is the z-score associated with this p hat? Or how many standard deviations above the mean is this value p hat, given my assumption that the mean is equal to that population proportion of 0.5 that we're assuming? So we're going to find the z-score that goes with p hat, just like we did back in chapter 6 in lesson 6.2, whenever we converted from x values to z-scores. That's exactly what we're doing here. We call that a test statistic. So we've graphed our sampling distribution. We've listed our sample statistic on that horizontal axis. And we're assuming that the null hypothesis is true, so we have some value of that mean for that distribution that we're looking at. And then we're saying, okay, that's a non-standard normal distribution. What would be the normalized version of that? What's the z-score associated with that? Now, for means, when we don't know the population standard deviation, we don't use z-scores, we use t-scores for the test statistics. For sample standard deviation, or for sample standard deviations, we're going to use another distribution called chi-squared. But the principle is the same. You're finding a value of a statistics corresponding to a particular type of distribution, either a standard normal distribution or a student t distribution or a chi-squared distribution, that goes with the particular value of the sample statistic that you got from your sample, that you were able to compute from your sample. So you're going to get that test statistic from the sample statistic. So we're converting from p hat to the corresponding z-score. And then once you have that z-score, you can find all kinds of things. You can determine the probability associated with that z-score. You can do something which is called finding critical values and compare your z-score to the critical values. So compare your test statistic z to the critical values. And based on where that test statistic stands relative to the critical values, you'll be able to make a decision about the null. Or based on the area in the tails, you'll be able to make a decision about the null. Remember, the area corresponds to a probability, and we want to reject outcomes that are associated with very low probabilities, according to our assumption, given that, well, they're happening. I don't know if that last sentence made sense. Let me start over again. We want to reject assumptions. I think I may have said the wrong word there. That's where my sentence went off track. We want to reject assumptions that lead to things that are happening in real life that correspond to very low probabilities. So you make some assumption, and then things that are happening are very, very improbable under that assumption. If that's the case, then you say, let's throw out the assumption. And remember, probabilities are represented by area under the curve. And we're going to be looking at area in the tails. So there are two options to make a decision about the null. One is going to be related to z-scores, and one's going to be related to that area or probability. But in each case, we are going to reject assumptions that lead to very low probabilities for events that are actually occurring. So one of those is the critical value method. The other one's the p-value method. And I know that was a lot. We're going to get into the details for both the critical value method and the p-value method toward the end of lesson 8.1. So just know that you're going to look at that distribution for your sampling distribution, and you're going to look at your sample statistic, and you're going to say, is that extreme given my assumption? If it's extreme, we're going to throw out the assumption. If it's not extreme, we're not going to throw out the assumption. And we're going to do that in one of these two ways, and we'll have the tools to do that later. And then finally, whenever you're conducting a hypothesis test, the last thing you want to do is state your conclusion in non-technical terms. Not everyone's had statistics. A lot of people aren't going to know what you're talking about if you start referring to z-scores and p-values, probabilities and areas under curves. But they will know what you're talking about if you say, evidence suggests that most people want to erase all of the data, their personal information that is available online. There was a study conducted, and it says this: whenever you read some Psychology Today or something like that, where they're telling you the results of some study in layman's terms, that's what we want to do for the readers of our statistical analysis. We want to make it very clear and very obvious to anyone who reads our conclusion what that study told us about the original claim. And that's number 7 here. Okay, now I wanted to point out that when we're doing this hypothesis testing, we're going to use technology. So we're going to use a little bit of Excel. We're going to use the Triola formulas and tables, and we're going to use pencil and paper a little bit. that the formulas and tables, pencil and paper, and Excel are going to allow us to find areas or probabilities and test statistics like z-scores and t-scores. And those are necessary to test, the various claims. But the focus is not on computation in statistics class. In statistics class, our goal is that you understand what it is you're doing and why you're doing it. That makes this very different from studying for an algebra class, where just practicing problems is the main, or is the best way, the best strategy to learn. In statistics class, you really have to make sure you understand the concepts. So you're going to have to study those like you would for history class. You're going to have to go over those over and over again in your mind so that you can keep track of all of the ideas. And of course, you don't want to just memorize those facts. You want to put them into your own words and make sure you truly understand them. So we're not going to worry so much about computation. You can use Excel, Triola formulas and tables, and pencil and paper. You can also use graphing calculators, TI-83 or 84 if you want to. I'm not going to show you how to do that in these videos. I'm not going to show you how to use StatCrunch or any of the other technology either. We're just going to use Excel because most people have access to Excel. But remember, the goal is not just that you can do the computation, but that you can understand the result that you came up with. I want you to understand what you're doing and why you're doing it, so that when technology gives you some output and they say, this is the z-score, this is the p-value, I want you to know what those values mean and what they infer about the original claim. So remember, when you're talking about hypothesis testing, the entire procedure is about determining whether the value of a sample statistic is rare, given some assumption, and that assumption is the null hypothesis, and some desired significance level. We're never going to be 100% sure of our conclusions. We want to be probably sure, not probably sure. We want to be 95% sure, or we're going to have a desired level of significance that we're going to talk about in other videos. But we can never be certain, but we want to be certain to a certain level, and that's called the significance level. And then lastly, if an event is rare and it's happening, we want to assume that the assumption that led to us saying that it was supposed to be rare was incorrect. And that's just the rare event rule. And this is our procedure for hypothesis tests. And hold on, I'm sorry, I have a knock at the door. I'll pause the recording and pick up where I left off in just a moment. All right, so we're just talking about the procedure for hypothesis tests. This is a great slide. It shows you an outline of the method as outlined in the statistics book by Mr. Triola. So you can see a zoomed in version of this if you just look through your statistics book, look through section 8.1, and it's there. It's a great graphic. Whenever students ask for help with hypothesis testing, I almost always just go to this list and say, follow these steps, and it's going to get you the right answer every time. Now, I still recommend that you watch these videos so that you understand why it is you're doing all of these things that are listed in this procedure. But this is a great way to remind yourself of what you're supposed to do if you get off track and you forget what it is you're supposed to do next. Okay, so our last example is one with drone delivery, and I just want to practice one more time. I'm writing the claim in symbolic form and then identifying the null and alternative hypotheses. So here's our claim. It says, given that at least 60%, given this claim, that at least 60% of consumers are uncomfortable with drone delivery, write the claim in symbolic form and identify the null and alternative hypotheses. Well, if they're saying at least 60%, that means that the proportion is equal to 60% or more than that. So proportion is greater than or equal to 60%, or in decimal form, we would write that as 0.60 if you prefer two decimal places. Now, if P is not greater than or equal to 0.6, well, then it has to be less than 0.6. So we write that down next. Whenever we're coming up with the null and alternative hypotheses, we always write the claim in symbolic form, and then we say, okay, if that's not true, what is true? Then P would be less than 0.6. And then now when you're identifying the alternative and null hypothesis, you look at these two and you say, okay, which one does not have an equals sign in it? And that would be this bottom one here. This one right here. It says P is strictly less than 0.6. Now, if you're saying that doesn't have an equals sign either, you're right, but the equals is implied. This says P is greater than or equal to 0.6. So this contains the condition of equality. That's what we say. This one does not contain the condition of equality. So that's our alternative hypothesis. And then the null hypothesis is just exactly the same statement, but instead of a less than sign, you want to have an equals sign there. Okay, so that's it for that learning outcome. I'll see you in the next video to talk about significance levels and type 1 and type 2 error for a hypothesis test.